Hi, my name is Seamus Coveney. I'm from Envo-Geo Environmental Geoinformatics, and I'm going to talk today about quality of the water lines. If you have any questions during the session, use the app and we'll address them in the Q&A. We're looking at the East Coast, and we're going to look in particular at Dublin Bay and Rosslare. Here's some sample water lines extracted from Sentinel-2 for Dublin and some for Wexford. First, we're going to look at qualitative assessment, particularly regarding the presence of residual cloud and breaking wave features that may present in the waterline data. Here's a good example of a clean waterline, and we have 46 in total, and of these, about 50% of them have almost no residual line segments that are attributable to clouds or breaking waves. But another 18 of them are of a similar level of quality, but some local patches of cloud and breaking waves occur that will need to be handled with post-processing. And a very small number then are good quality in certain locations, but occluded by cloud in others. When the algorithm is run, there's a number of internal tests applied. One of them is a line length test, and essentially longer line lengths tend to correspond with waterland boundary segments, and shorter ones tend to correspond with transient features, clouds, breaking waves. They also run a line confinement index test, which applies a score similar to the line length test. And what it does is it looks at the ratio of the length of a line segment relative to the map X and map Y distance in essentially a minimum bounding rectangle that would confine that line segment. Shorter line segments tend to be actual waterline segments. Longer, more squiggly ones tend to be associated with waves or clouds. The advantages of both are combined, and a new score is generated using a blended approach of both results. And basically these scores can be used to aid the post-processing procedure, which will be applied later. Here's the line length test in pictorial form. Circled here are lower scored shorter line segments that are basically clouds. Some more cloud fragments here, and we have some longer sections here. One is waterland boundary, and another is actually a cloud. So none of these tests are perfect, but they actually are very useful, particularly when they're combined. The line confinement test. Here are some long squiggly segments that correspond with clouds, and longer, smoother segments that correspond with waterland boundary. When they're combined here for Dublin, those greener lines are the higher scored results, and the shorter red ones are the lower scored results. And basically these lower scored results can be filtered out by query, requiring less manual interaction in the post-processing cleanup phase. A heat map analysis is also run when all the water lines are generated, and basically what this does is it overlays all of the water lines, and in essence it operates on the logic that repeating line segments will tend to be associated with actual waterland boundary, and transient line segments will tend to be associated more with clouds and waves. And there's a model. And variations in waterline position that are related to tides are accounted for by using a fuzzy linear membership function, 100 meters either side of a line, of a line segment that is likely to be, that is occurring frequently, will be assigned scores, basically. So the more often line segments overlap, the higher their score. The less often they overlap, the lower the score. And this produces an additional score that can be used to aid in the post-processing cleanup. Here's the input data, 26 to 2020. The red portions of line segment are clouds and waves predominantly, and the greener segments are the higher scores that come from the LCI and the line length tests. When the fuzzy classification is run, this is the output. It suppresses all of those lower scored data, and the lighter colors here are coincident with steeper coasts where less change occurs tidally, and the darker ones are tidal zones. But this is useful delineation also in terms of aiding the process of cleanup. We're going to look at positional accuracy here. We're looking at Ordnance Survey absolute, relative, and geometric fidelity. Assessments for map accuracy from Ordnance Survey. Here's our sentinel image for Dublin. We're going to zoom in on Dun Laoghaire Pier. Reason being, it provides vertical structures that provide an interface with the water boundary, regardless of tide height. And we're zooming in at a sub area here, and we're going to look at horizontal offsets between the red waterline and reality, which is an Ordnance Survey 25 centimeter ortho image. And we're seeing horizontal offsets of the order of 5, 10, and 15 meters, which corresponds with about half of a 1 pixel, 20 meter pixel, so roughly on average 10 meters in our initial test here. Looking at Wexford, we're seeing similar horizontal offsets, and some of them larger, and we started to wonder what might be the explanation for this initially. And what we noticed is that on the western side and northern side of tall features, deviations are larger, which may be related to the presence of shadow. Because we have southeast illumination, these sentinel images are acquired over Ireland at basically noon. So shadowing might be an effect here. That's particularly noticeable where you have shadows coming from two sides potentially. Less so on east-facing illuminated edges. And given that the East Coast is east-facing, maybe the problem is less to be expected along the vast majority of that coastline. Looking at relative accuracy, what we're looking at here is the relative length of features represented in the waterline data relative to reality, and reality is our Ordnance Survey imagery. And what we're finding is a close match in both test locations. Geometric fidelity, which is the shape of features represented in the waterline data relative to reality, again a close match, but with the proviso of the absolute offsets that we noted and discussed previously. Next thing we looked at, something to consider here, is the waterlines do not contain attribute information when they come out from the algorithm. That's a further step that has yet to be undertaken. So what we did is we wanted to do a quick test, to see if a tide gauge attribution compared reasonably well with GNSS survey data. We have 4 images and waterlines for 2019 that overlap some of our recent 2020 GNSS surveys, dual frequency GNSS, high accuracy data. And we looked at our 4 waterlines, looked at the satellite time, and we looked at the nearest 5-minute interval tide records, and we converted the tide height recorded at these time stamps to ellipsoidal height using Grid Inquest Ordnance Survey software, and then we compared that with the mean GNSS measured height within 2.5 meter radius of the waterline, and we have 4 locations where we have overlaps with the GNSS profile. And what we see is vertical offsets of the order of about 1.5 meters in all 4 locations. And when we compare with Wexford tide data, we see vertical offsets of the order of 1.25 meters in all 4 cases. So in summary, qualitative assessment, the output from the algorithm, generally speaking, produces good, clean water lines, and it scores all line segments in a manner that enables us to remove the lower quality line segments attributable to waves and clouds, etc., by query, and requiring less manual interaction. Positional error metrics, in summary, of the order of about half a pixel in what we've seen so far. When we look at height, comparison to tide height, with GNSS height, we see vertical offsets of the order in our initial tests of 1 to 1.5 meters. Generally speaking, the output of the algorithm looks to be performing very well along particularly on the east-facing coast, where there's no substantial problem with illumination and shadowing because it faces east. In terms of future work, next steps are post-processing cleanup and water level attribution. Thank you for your attention.